Hi everyone and welcome back to our YouTube channel. In this lecture, I will show you a practical application of systems of linear equations that is used in the field of electrical engineering. And our problem is to analyze a given circuit. And by analyzing, I mean how to find the voltage values or the current values at any point of the circuit. And to do so, we use two main laws known as Ohm's law and Kirchhoff's laws. And first of all, let's see what these laws or rules are talking about. First of all, let's start with the Ohm's law. And while V is the potential, in other words, the voltage difference across a resistor measured in volts, and I is the current that is flowing through the resistor and measured in amperes, and R is the resistance of that circuit element measured in ohms, we have the famous formula V is equal to I times R. And what this means is, if you want to find the voltage across some resistors, then we need to multiply the current that is flowing through it by its resistance. This is the Ohm's law. Okay. And let's see now, what does Kirchhoff laws say us? Okay. And Kirchhoff rules can be considered in two pieces of rules. The first is called Kirchhoff's current law, in short KCL, and it depends on the conservation of charge at a node. And what this says is the sum of the currents flowing into a node equals to the sum of the currents that is flowing out of that node, and this case is called the nodal analysis. That's why called nodal analysis, because we try to actually find the algebraic sum of the currents at a specific node, and we know that due to the conservation of charge at a given node, this algebraic sum should be equal to 0, and this is called Kirchhoff's current law. And another law says that which is called Kirchhoff's voltage law, if you travel once around any loop and add up all the voltage rises and drops, then this algebraic sum is equal to 0. So we have a loop here, and then the sum of the algebraic sum of this voltage changes across this loop is equal to 0. And this is also called the conservation of energy around a closed loop. And in other words, Kirchhoff rules state both conservation of charge at a given node or conservation of energy around a closed loop, depending on the type we analyze. So the first one is called the nodal analysis because we take into account the currents at a node. And the second rule is called a mesh analysis because this time we actually take into account the voltage drops or rises across a loop, across a closed loop. All right, before proceeding to example, let's first understand some terminology, because in nodal analysis and in mesh analysis we use some terminology, namely a node and a mesh, and what these are. And a mesh actually is nothing, or a loop, you may say a loop or mesh, is actually any closed path in a circuit that starts and ends at the same node. And that is, you start with a point, or you start at a node and then just follow the current through a closed path, and if you reach to the same point, then you have a closed path which is called a loop or a mesh. And the node is any point in a circuit where two or more loops or meshes are connected. So actually, to find a node, you look at the intersection points of these different meshes or loops. Alright, after defining this basic terminology, well, let's first understand how we really choose these loops and meshes. For instance, suppose we are given the circuit shown in this example, then what are the here nodes? Well, for you, I already selected the nodes. For instance, V1 is a node. Why? And V2 is a node. I will come to that point where I will explain why. These are the nodes and this one, and also there is one more which is considered to be grounded, so it is connected to the ground. So actually there is one more, but I didn't take into account that. Say it V4. So, and a loop actually is a closed path. We start at a node, and then as you see, when I start at V1 and follow this circuit and then follow this direction, as you see, if you follow this black arrows, so I come back to the same point, and this one is a loop. And another loop is that, for instance, look at here. So this is another loop, right? So we have another loop here. Why? Because I started at some node, which is the intersection point of different meshes, and then I make my way up, all the way up, and then turn right and go below, and you see I come back to the same node, and this is another loop. So this is how we decide what are the loops and what are the nodes. And another loop here is, you see, we have one more loop here, so one loop here, so this is actually, and another loop here, right? So you see that we have another loop here, so we have 3 loops because we have 3 closed paths, conductive 3 closed paths, and we have actually 4 nodes because V1 is the intersection point of more than one meshes. You see, it is placed at the intersection point of this loop and also this loop, so it is a node. And V2 is another loop, right? Because it is located right at the intersection point of these 2 meshes. And V3 is another one. And so we are given actually in this electric circuit 4 different nodes, but I select one of the nodes, which is V4 in this case, as the reference node, or it is called a datum node, which is connected to the ground. So, and then I use the remaining n-1 nodes, which is 3 different nodes in this case, V1, V2, and V3, to analyze my electric circuit. Alright, so now I know what are the nodes and what are the loops for this given circuit. But how then, one simple question comes to mind, that how will I analyze this circuit? In other words, my question here is that find the voltages at each node. That means I need to find the voltage value, the values of the voltage at V1, V2, and V3. So how can I do that? And here in this example, my main goal is not to teach you all the circuit theory, but instead to show you how we can convert a problem, a physical or electrical problem, into that of a problem we are familiar with. And what is problem? And this problem is solving the systems of linear equations. And to analyze this electric circuit, I will convert this problem into a system of linear equations by applying the laws, Ohm's law and Kirchhoff's rules on the circuit. To do so, guys, I need to follow some basic steps, and which I actually summarized here for you. And these steps are, first of all, I need to identify all nodes and loops. And I select one of the nodes as the reference node, which is grounded, so which is actually connected to the ground to neutralize the circuit. And then I will use Ohm's law to express voltage across resistors in terms of currents. So I make use of Ohm's law. And then to convert this problem into equations, I will either use KCL equations at nodes or KVL equations around loops. And this is nothing but related, actually this step is nothing but something related to the Kirchhoff rules. I will either use nodal analysis or mesh analysis, or in other words, I will either find the currents at a node and then convert them into equations, or I will focus on the loops and then write the voltages and then turn them into equations. So I have two options here. I will apply either nodal analysis or mesh analysis depending on my choice. And after then, since now I have a system of equations to solve, I start solving the system and find unknown variables. So my unknown variables could be either voltage values or current values depending on what is asked to me to find. So here in this question, I am required to find the voltage values at each node. Alright then, after summarizing you the steps that we should follow to analyze this electric circuit, let's start to apply these steps. Now, the first thing to do is we already have identified the nodes and loops, and we will actually have three different equations. And how would I understand that? Because as you see, we have three nodes besides the reference node, so I need to convert them into equations. So I will have three equations in the end, but the problem is how we will construct these equations. Okay, let's see how we can do that. Alright, so first of all, since I am required to find the voltage values, then which rule I should use? Well, in this example, I will use the Kirchhoff's current law. Well, in other words, I will continue by assuming the conservation of charge at a node. And at each node, I will rewrite the currents to form an equation. Okay, let's see how I can do that. Let's start with the first node, V1. And let's do that. Okay, here is V1. Alright, so at V1, we are at V1, and I will use the Kirchhoff current law. And what the Kirchhoff current law states? It states that the algebraic sum of currents at each node is equal to 0. So here's the thing. 10 amperes goes up here, you see, to node 1. And some of this current makes right, whereas some amount of the current goes up. And I don't know how much of it goes up or how much of it makes right, but what I know is I can give them some names. And for the V2, at V2, as you see, we have this and 20 amperes over here, so some of this goes up and some of this makes left. And at V2, some of this current goes down. So how would I understand that? I just follow the direction of the flow of current, right? So it goes up and it will either turn right or go up. Or in this 20 amperes case, it will either go up or turns left. And at node V2, there is the current flowing into that and also flowing out of it below to the reference node, to the direction of the reference node actually. Alright, so I need to give some name. So for instance, well, I need to construct equations, and to have equations I need unknown variables. Say for instance this current value is equal to I1, say it I1, right? And let's call this one I2, so I give a name to each current value, and let's say this one equal to I3, okay? And I represents the current, and I just give some number, so depending on the number of different currents. And let's continue this way. And what can we do here? Let's say this one is I4, and let's this one be I5, and I have two more. Let's say this one I6 and I6, and this one I7, right? Okay, now things become a little more clearer here. So I can now write equations, for instance, at node V1. So I look at the incoming current. What is the incoming current at node V1? So the only I look at the direction of the flow of the current. If it comes through the node, in other words, if it comes in the node, then it is a flowing in node, so flowing in current. But if it is coming out of the node, then it flows out. So the thing is, the algebraic sum of the incoming flows should be equal to the algebraic sum of the outgoing ones. So what I can do is, since E6 is the only incoming flow, then E6 should be equal to I1 plus I7, right? So this is my first equation. And how about at node V2? So I applied Kirchhoff's current law. So at each node, I know that the algebraic sum must be equal to 0. And how can I understand it? If I move I6 here to the right hand side, then this is equal to 0, right? And at node 2, so what are the incoming currents, right? I1 and I2 are the incoming currents, so I1 plus I2 should be equal to the outgoing current, which is I3 in this case. So this is the second equation in terms of the currents. And how about node 3? Well, at node 3, what we have? What is the incoming current? And the incoming current is I4. So I4 is equal to the algebraic sum of the outgoing currents, which are I2 and I5. I just write them. I2 plus I5. Alright, now I form the basis of my system of equations. Now I applied Kirchhoff's current law to have some equations, and as you noticed, at each node actually I use the conservation rule, right? Because now conservation of charge at each node is applied. So this is actually what it means for the first rule of Kirchhoff's rules. And what should I do now? But the thing is, all right, now I have an equation for each node, but this is not what I am trying to find. Look at the question. I am required to find the voltages at each node. But right now, I only have equations in terms of current values. And with respect to these equations, the unknown variable is the current, right? But our unknown variable should be the voltage because we are trying to find the values of voltage at each node. And how can I do that? Well, the second step is now it is time to apply Ohm's rule or Ohm's law, right? So now we will apply Ohm's law at each node. In other words, in each equation, I replace the values of currents with the Ohm's law. And what it means, we know that, right? We know that V is equal to I times R. And if you isolate I here in this equality, then I is equal to, in other words, current is equal to voltage over resistance, right? So if I divide voltage by resistance, then I have the current values. So in each equation, if I replace the unknown variable I's by its equivalent V over R's, then I will actually have a system of equations in terms of voltage values. And this is a good sign. So let's do that. So for the first equation, again, right, for my first equation, let's apply this Ohm's law. Okay, let's start with I6. So what is the value of I6? Well, there's 10 amperes just flowing through here, so I6 is equal to 10 amperes, but nothing, right? So it is simple. So I write 10 is equal to, now what? I1 plus I7. But the problem here, there's actually one problem here, okay? In other words, if you notice, we have a problem coming out of this situation. So I need to find I1. But what is the value of I1? So look at the current I1. So look at the flow of this current. Actually, it starts at node V1 and then it goes all the way to node V2. So actually, the voltage, I need the voltage value, and the voltage is the difference through this resistor, right? Which has a resistance of 1 ohm. So I start with node V1 and I end with node V2. So the difference is V1 minus V2. I just follow the direction of the current, right? So I look at in which direction this current flows and I take the difference. So I1 flows from V1 to V2. So when I write it by using Ohm's law, then what I have here is like the voltage across that resistor is equal to V1 minus V2 over the resistance. And the resistance is 1 ohm. So I just put its value. And how about I7? Well, I apply the same strategy. I use the Ohm's law and the definition of voltage. Now we have I7. And where is I7? I7 goes up, you see. But where it starts, at which node it starts and at which node it ends, I just follow this direction. So I7 starts from V1 and goes all the way through V3, right? So the first node it ends up here is V3. So I take the difference between V1 and V3. And in this manner, I will be able to actually compute the voltage that is passing through this resistor here, right? So this 1 ohm resistor. So what is the result? So V1 minus V3 over 1 ohm, right? This is also 1 ohm. So let's write it. Again, V1 minus V3 over 1. And dividing by 1 yields the same value in the numerator, right? So, well, I'm just showing you because this is the first example about that. Okay, so now what we have? So what we have here is an equation in terms of the unknown variables which are VI's, right? The voltage variables. So what I have is 2V1 minus V2 and minus V3 is equal to 10, right? This is the first equation that we come up with by applying both Kirchhoff's current law and Ohm's rule, right? We applied both laws. Okay, and I will continue in this manner. Now I will have two more different equations for the V2. So we have I1 and we have I2, right? So how about the I1? So I1 is, again, look at the voltage difference, V1 minus V2 over 1. So the same thing. Okay, so I write it here. V1, we are at node 2, V1 minus V2 or 1. I don't write 1 again. And for I2, how can I decide I2? And again, applying Ohm's rule, look at the direction of I2. So the current I2 flows through V3 to V2. So we take the difference between V3 and V2, right? So this is nothing but plus V3 minus V2, and the current passes through. And one important thing to remember, I2, this current is passing through the 1 ohm resistor here, so that's why I divide by 1. So be careful about that. It depends on the circuit element that the current flows through. And what is the value of I3? Let's look at I3, where it is. So I3 right here. You see I3 is right here. So we have V2, it starts at node V2 and it ends at node V4, but V4 is selected as the reference node. So the voltage there is equal to 0. That's why it is grounded, right? It is connected to the ground. And the voltage rise or drop here is equal to 0. So it's like V2 minus 0, which is equal to V2. How about the resistor resistance? So resistance is equal to 4 ohm, right? Because it passes through, well, the current is passing through actually 4 ohms resistor. So what we do is, this is equal to V2 over 4, right? So this is equal to V2 over 4. And multiplying by 4, so what we have here, and then putting the same unknown variables in the same place, we have an equation, we have a new equation, right? So we have 4V1 minus 9V2 and plus 4V3 is equal to 0, right? And this is the second equation. And again, guys, if you notice that we again reach to an equation where the only unknown variables are the voltage values as required, because we will be trying to find the voltage values, right? That's why I use first Kirchhoff's current law and then Ohm's law and define the current values in terms of voltage values, which are the only unknown variables here. And we have the second equation. Now, there's only one thing left behind this. So if we are able to write the third node in the equation form, then we have our system. And let's do that. Again, we use the same strategy. We look at I4. And I4 what? If you notice that I4 is, you look at this. If you look at this here, I4 is right over here. and it is 20 amperes, right? The current here, we have a current source here, so it's 20 amperes. So we know the value. So I4 is equal to 20. I just put its value here. So let's write it down here. I4 is 20, and 20 is equal to what? Now I need I2 and I5. And what is I2 and I5? And I2, again, we just found it in the earlier step. We take the difference between V3 and V2, right? Because the current flows through V3 to V2, right? So V3 minus V2 over 1 again. So let's write it. V3 minus V2. And we also need to have I5, right? What is I5? Let's look at what it is. Where is I5? Well, I5 starts at node V3 and passing through the 1 ohm resistor here and ends up at node V1. So we take the difference between V3 and V1 and divide it by 1 ohm. So let's write it down here in the same manner. Plus, let's say V3 minus V1 divided by 1 again yields the same result, so I don't write the denominator values because they are equal to 1. It doesn't change the results, so I put them in the algebraic form. When I sum them up, then what I have here. So let's see what we have. Finally, we have minus V1 minus V2 and 2V3. 2V3 is equal to 10. Sorry, is equal to, right, 20. Right, 20. All right. Yes, that's the value 20, right? So there is no numerical error. I just checked it out, and then let's give a name to this equation. Now we have the third equation here. So what we have? All right, guys, if you notice, now we have a system. If you look at here, this is the first equation we just find, right? That's what we have found here. And this is the second equation with respect to the unknown variables, which are the voltage values, and the third one is as well. So what is left to do for us is, now we have the system of linear equations, and what we are trying to find the voltage values as desired. So the only unknown variables in this system is the voltage values that we will try to find. And what we need to do is, by applying one of the techniques we know, we will try to solve the system, right? So we will try to solve the system. Well, first of all, if I prefer applying Gaussian elimination method, then I just write the augmented matrix form here. So, and let's put the coefficients 2, minus 1, minus 1, and 10 for the first equation. And for the second equation, what we have here, this is 4, minus 9, 4, and 0, right? And for the third equation, we put coefficients here, minus 1, 2, and 20. Okay, this is the augmented matrix form, right? As we all are familiar with. And I check to see whether or not it is in row echelon form, because I will be applying Gaussian elimination technique, and what this means is I need to convert this matrix into its row echelon form. And so first of all, I need to eliminate the values below the first pivot element, and our first pivot element is the first non-zero element in the first row. So to do so, I need to replace both row 2 and row 3. So let's perform elementary row operations, and for the row 2 case, I replace row 2 by row 2 plus minus 2 times row 1. And for row 3, what should I do? I need to replace row 3 by row 3 plus 1 over 2 row 1. And then our new matrix becomes, let's see what it becomes. Okay, so the first row remains unchanged. I put its values as they are, but the second row and third row have changed their values. So now we have 0, minus 7, 6, and minus 20. And for the third row, we have 0, minus 3 over 2, 3 over 2, and 25. Yeah, 25. Alright, again, after I am done with each elementary row operations, I check to see whether or not our matrix is in the row echelon form, and you see, well, I am done with the first column, but I find the second pivot element, and I see that the value below the second pivot element is not equal to 0, so I need to eliminate minus 3 over 2. So this value should turn into 0. So I'm not done yet. So one more step, then I need to replace row 3 by something else. So row 3 replaced by row 3 plus minus 3 over 14 times row 2. So I actually, how do I find this minus 3 over 14? Okay, I look at minus 7 and minus 3 over 2. So I'm trying to find a real value that when I multiply it by minus 7 and sum it with minus 3 over 2 and replace the third row by this new value, then this new value should be equal to 0. So that's why I multiply minus 7 by minus 3 over 14, because if you notice, when I multiply them, it is equal to 3 over 2, and when I add it to minus 3 over 2, then it's equal to 0. This is how I decide. So I continue with the process again, right? So I continue. So we have 2 minus 1 minus 1, 10, 0, minus 7, 6, and minus 20. And what we have in the last row is 0, 0, 3 over 14, and the last entry we have 410 over 14. Right. And again, I check to see whether or not we're done with the Gaussian elimination process. And yes, we're done, because now starting from top row, ending with the last row, we have a strictly increasing number of zeros. And then we're done with the Gaussian elimination process. So now what should I do is, I apply back substitution method to find the unknown values, starting with the very last row. So the first row actually represents V1, the first column represents the first unknown variable V1, and the second column V2, and the third column represents V3. So, and the last column represents the right hand side values. And again, in the last row, what I have is 3 over 14 V3 is equal to 410 over 14. And as you notice, by applying back substitution method, when 14s are cancelled out, well, we have found the value of the third unknown variable, the third voltage value, which is actually the voltage rise or drop at the third node given in the circuit, right? So 410 over 3 is something around approximately 33.61. And continuing in the same manner, we can find other values, right? In the second row, again, I put the same values. This time, the only unknown variable is V2, and in the first row, the only unknown variable is V1, and we can find this unique solution. And by the way, with respect to this augmented form, in other words, actually, with regard to the row echelon matrix, we found we have a unique solution case, right? We can understand that simply. Okay, so when we replace back the values, we have only one solution that guarantees that we have the unique solution case, as we already know. And in the same manner, we have V2 something around 27.95, and V1 is equal to, 29.28. You can also round it up or round it down, these numerical values, but I just left them as they are. So these are actually the values that we were looking for in the beginning. So we have found them, right? What are these values? These are the voltage values. Okay, now look at this point. So I have found all the voltage values at each node for this given electric circuit. Alright guys, I hope that you enjoyed this practical application that we use to analyze a given circuit. Well, in this example, I used the nodal analysis and I used the Ohm's law, but it is also possible to apply the mesh analysis as well. But when I apply the mesh analysis, then this time I just find the algebraic sum of these voltages, and then this time I will have an equation for each mesh in terms of current values. Well, we apply a similar procedure just in the reverse way. So in this example, when I use nodal analysis, I have a system of equations where the unknown variables are the voltage values. But when I use mesh analysis, then we change the roles between voltages and currents. This time, since I will be finding the algebraic sum of voltages, then I use the Ohm's rule or Ohm's law to define each voltage in terms of currents. Then I will have the currents as the unknown variables in each equation. So it's just a exchange between the roles. Alright, that's it for this lecture, and see you in the next lecture, guys.